So for a one-dimensional particle that's described by some wave function, psi of x and t, in some potential v of x, we know that this condition must be true. Psi star psi, if we integrate that over the entire one-dimensional universe, this must be a constant. In fact, it's a particular constant. It's equal to 1, right? That's the normalization condition. So it must also be true that if we take the time derivative of psi star psi in dx, we take the time derivative of this quantity, that must be equal to 0. In other words, if the function is normalized, it's normalized for all times. That's not going to change with time. So let's look at what this implies from the perspective of the Schrödinger equation. Let's see that this can be translated into a condition for the Schrödinger equation, because when we take time derivatives here of these terms, the Schrödinger equation is an equation that has d psi by dt and d psi star by dt in them. If we look at the star complex conjugate, so let's do that, and therefore let's do d by dt of minus infinity to plus infinity of psi star psi in dx. This is the integral of, right, we're going to apply this to this term, and so we have the chain rule. We have d psi star by dt times psi plus psi star d psi by dt in dx. But these terms, these time derivative terms, they can be written in terms of spatial derivatives by the Schrödinger equation. Right? So we have, so let's not write out the Schrödinger equation. Again, we've seen this before. We get, by virtue of the Schrödinger equation, I h bar over 2m times the integral minus to plus infinity. We actually have two derivatives of psi, and then we have potential terms. We won't go through that all over again, but we'll break this up as we've already done before into two terms, psi star d psi by dx minus d psi star by dx psi in dx. Right, so just to reiterate, when we apply this to this one and this to this term, we get those things cancel out. But so the ones that survive are psi star, two derivatives of psi with respect to x, and two derivatives of psi star with respect to x times psi. And those are just related to the Schrödinger equation with this, right? So this term here is going to be related to the two spatial derivatives of psi star, and this term will be related to the two spatial derivatives of psi, and of course psi star goes along for the ride here, and psi goes along for the ride with this term. So you can see that, and then the potential terms will cancel out. So we integrate these, right? We write it like this so we can see that when we integrate this, we'll just get the thing in parentheses. And so that looks like I h bar over 2m times psi star d psi by dx minus d psi star by dx psi, and we evaluate this from minus to plus infinity. And so all we need to notice here is that these functions, right, since psi star equals psi equals 0 at plus minus infinity, then this whole thing then, well, I don't want to write the whole thing again. Let's just rewrite then this whole calculation, time derivative of that must be equal, in fact, to 0. So we already noted that psi star and psi, if they don't go to 0 at infinity, at plus or minus infinity, then we can't even normalize the wave function. Right, so the fact that we can normalize it then ensures that it remains normalized in time.